Welcome to This Explainer. I'm so thrilled you're joining us today. We're about to embark on a totally fascinating journey through the world of silicone chemistry. We're going to trace the entire lifespan of these incredible materials, literally starting all the way down at the microscopic molecular building blocks, and then working our way right up to the high-performance, real-world applications that, honestly, power our modern lives. Whether you're deeply involved in materials science or, just super curious about the hidden engineering all around us, this explainer is designed to give you a really clear, structured look at exactly how silicones work.
Okay, let's dive right in. Here's our quick roadmap for today's explainer. We'll start with a welcome to silicone chemistry, then look at the silicone chemical structure. Check out chlorosilanes as our building blocks. Go over hydrolysis and polycondensation, and finally, wrap up with high-performance silicone elastomers and the amazing versatility of silicone fluids.
So, Part 1. Welcome to Silicone Chemistry.
Now you might be wondering, why dedicate an entire explainer to this one topic? Well, it's because silicones are kind of the invisible, highly engineered materials that keep our modern lives running. At their core, silicones are inert, synthetic polymer compounds. They beautifully combine silicon with carbon, hydrogen, and oxygen. And it's exactly this incredibly flexible chemistry that gives birth to just a massive variety of forms. I mean, we're talking materials robust enough for heavy-duty automotive engine parts, but also biocompatible enough for something as delicate as a baby's bottle nipple.
This totally unique makeup grants them what I like to call superpowers. You can actually see it in action with their striking, water-repellent beating effect. But hydrophobia is really just the beginning. The true magic of silicones? It's their ability to survive absolute extremes. We're talking about maintaining a flexible polymer chain down to -100 degrees Celsius, while also offering incredible thermal stability all the way up to 250 degrees. They literally laugh in the face of oxidation and UV rays.
Moving on to Part 2, the silicooxane chemical structure.
To really grasp how silicones achieve these extreme superpowers, we've got to zoom in a bit. The secret lies in the silicone bond. The basic structure is made of polyorganosilicsanes. That's basically silicone atoms linked to oxygen to create a strong core backbone. The remaining valences then link up to organic groups, most commonly methyl groups, which creates polydimethylsiloxane, or PDMS for short. This structural foundation actually allows the polymer chains to freely glide and slip over one another, and that exact mechanism is what creates highly flexible, flowable fluids, even when you subject them to extreme temperatures.
All right, Part 3. Chlorosilanes, the building blocks.
So how do we actually create these materials in the real world? Well, if you think of chemistry a bit like playing with Lego blocks, chlorosilicons are our raw starter Lego pieces. They are prepared through a process called direct synthesis. Basically, this involves reacting natural silicon powder with methyl chloride gas inside these absolutely massive reactors. It's actually pretty wild to think about, right? This violently explosive reaction eventually gives us the perfectly safe silicon used in baby pacifiers. Anyway, this reaction creates a crude liquid mixture of different chlorosilicons. These raw liquids are the absolute foundation. Every single silicon substance starts with these central silicon atoms bonded to varying numbers of chlorine atoms.
Which brings us to Part 4. Hydrolysis and polycondensation.
Now we need the actual industrial steps that transform our reactive Lego blocks into basic silicone commodities. Think of this as a step-by-step roadmap. Step 1 is direct synthesis, which, as we just covered, gives us our chlorosilanes. Step 2 is hydrolysis. By introducing water, the chlorine atoms provide reactive sites, snapping the pieces together to form the siloxane backbone as short-chain polymers. And finally, Step 3 is polycondensation. By using catalysts, this step lengthens those chains to the exact required molecular weight. By carefully controlling these steps, chemists literally become architects of the molecular framework.
And the silicone family tree brilliantly illustrates the macro result of all that chemical processing. Notice the visual fork in the road. Through hydrolysis and polycondensation, our raw chlorosilanes are transformed into core products, basically gums and oils. From there, those basic commodities formulate into two massive, totally distinct specialty families: elastomers, which come from the gums, and fluids, which come from the oils.
Let's zoom back out to the macro world for a second and compare these two distinct end product families side by side. On the one hand, we have elastomers. These are your solid, rubber-like materials. They're highly elastic, they boast incredible tear strength, and they're compounded with cross-linking agents and reinforcements, like silica, to handle really heavy mechanical stress. On the other hand, we have fluids. These include your oils and resins. Remember those chains we talked about that glide and slip? Well, that's exactly what happens here. resulting in highly versatile, flowable liquids that maintain their properties across a huge range of viscosities. Their contrasting physical forms totally dictate how they're used in the real world.
Let's look closer at Part 5, high-performance silicone elastomers.
Okay, let's dive deep into that first major branch, the solid, highly elastic elastomers. Actually, I want to ask you a quick question. With so many synthetic rubbers out there, why do highly demanding industries specifically choose liquid silicone rubber, or LSR, over traditional alternatives like NBR or EPDM?
The answer really lies in its precise, unbeatable performance characteristics. Consider the crazy diversity of its applications. In the automotive industry, LSR is the go-to for harness sealing and gearboxes. Why? Because of its high tear strength, low compression set, and incredibly stable self-oil bleeding capabilities. It protects complex parts from severe mechanical stress and aggressive chemical fluids. But then, if you flip to the complete opposite side of the spectrum, LSR's exceptional harmlessness and biocompatibility make it the ultimate material for medical applications, like catheters and even everyday infant products. It cures incredibly fast, it's highly precise, and it survives extreme temperature variations without breaking a sweat.
And finally, Part 6. The versatility of fluids. Shifting over to the other side of the family tree, let's take a look at the incredibly adaptable silicone fluids. Now, we know standard silicone oils feature a high density of methyl groups, which is what allows the chains to slip. But here's the really fascinating part. If chemists replace just a minority of those methyl groups with different organic functionalities, say phenyl to make it heat stable or vinyl to make it reactive, it completely modifies the fluid. Suddenly, this base oil takes on entirely new, highly specialized characteristics. It's like upgrading its software.
Because of that highly customizable chemistry, silicone fluids have an unavoidable and just incredibly versatile presence in both our daily lives and in heavy industry. Depending on exactly how they're formulated, whether that's as resins, emulsions, greases, or compounds, they serve as everything from the tackifier in pressure-sensitive adhesives to the water repellents protecting buildings and textiles. You'll find them acting as additives in your everyday home care products and cosmetics, all the way up to heavy-duty industrial emulsions used in agriculture, oil and gas, and wastewater treatment. They are literally everywhere.
Well, that brings us to the end of our explainer, and I want to leave you with a bit of a provocative thought. We've seen how a surprisingly simple reaction of silicon powder and gas creates a material that literally seals our car engines and safely constructs our medical devices. So, as we move rapidly toward intelligent, networked industrial processes and highly advanced long-term implantable healthcare, where will silicone chemistry evolve next? These invisible polysiloxanes are truly the unsung heroes of modern engineering. I really hope this structured journey has given you a powerful new perspective on the materials shaping our world. Keep learning, keep questioning, and thank you so much for joining me on The Explainer.